Hi everyone, and welcome to another day of CS202 Online. Today, we're going to be talking about dynamic variables. It's like, where did I go? There I am. Okay, so last time we were talking about pointers, and the last thing that we kind of finished the topic with was talking about the null pointer, and basically you wanted to set your pointers at null. And so I've given you this whole thing about pointers, and we didn't really ever say the why. So like, why pointers? Like, why introduce the whole concept of pointers? And well, one thing that you could argue for is you have what's known as aliasing, right? So now you have the ability to have a variable that can be referred to with different names or identifiers, right? So you can have a variable x, like int x gets 5, and then set a pointer, like int asterisk ptr equals the address of x. And so now you can refer to the contents that are located at x using x, but also using ptr. So this might be like, why would I want that in the first place? There's some cases where that actually becomes really convenient. And particularly when we start talking about like array implementations of things that hold pointers, it comes in pretty useful to have that. But it's not really the main reason why you use pointers. So, and like, you could totally get around doing all of that nastiness of having aliasing and just not use pointers at all. However, there is one big thing that you should be using pointers for, and that's this topic, dynamic variables. That's the real reason pointers exist. So what are these dynamic variables? Well, I'm glad you asked, because I'm about to tell you. All right, so let me go ahead and just kind of define it first. So basically, again, the topic of today is why pointers. And the answer is dynamic variables, as you saw up there. And so dynamic variables are defined as variables that are created during runtime, essentially. So variables that are created during runtime, or also known as program execution, during program execution. So when the program is actually running in the computer, not when you're compiling it and not when you're coding it, but when it's actually running. So the variables that are created at this point are basically known as dynamic variables. And the way you create these dynamic variables in C++ is with the help of pointers. Other languages work differently, so this applies to C++. For example, everything is dynamic in Python, so all variables are dynamic there. I'll abbreviate dynamic then. Okay? So ultimately, if you're looking to create a variable at runtime, that's when you want to use pointers. Now, why would you want to create a variable at runtime? Well, this is the thing I actually introduced when I was talking about pointers, but I'll re-emphasize it now. So far, all the arrays you've made, except if you use vectors, but if you didn't use vectors at all, which is not something that we use a lot. I mean, well, we use a lot in these classes, but in the real world, we do use a lot. But like in these classes, 135 and beginning of 202, you're not really using a lot of vectors. And I do have some videos on vectors if you want to check them out. And they are good to know because you do use them often in the real world, if you're using C++ at least. But what you typically do in 135 is you just make kind of like a static array, in the sense that you decide how big the array is at compile time. So you say something like int m5, and that means that m is a variable with 5 elements in it. And it's cool if you know you're only going to be using 5. In fact, if you're always using 5, then it's perfect. If it's a variable amount you're storing there at a given time, as long as the limit is 5, the upper limit, then you're good to go. But suppose that you had a program that needed a lot of memory in the beginning, maybe to reading a file into some data structure, some array. And then after it did some processing, it didn't need it anymore. If you code it the way you've been coding so far, you make that using a static variable. That space will be allocated the entire time the program is running, from start to end, because you coded it that way. And it's fast because once you actually do allocate the space, it's already there for you, so you can go in and out of it quickly. It's all good. The downside is that it takes space. That takes the whole space it needs at all times when it really doesn't need that much space. Now, the programs you've been doing so far are little children, like kiddie programs that are using bytes of size. Kilobytes is already like your upper limit of the amount of space you probably used in a single program. But if we get real for a second and start talking about something that's bigger than kilobytes, we get megabytes, gigabytes, or even terabytes. And that is possible that you could be loading something like that, at least at the gigabyte level, because we have, yes, there's computers with terabyte RAM, but gigabytes is more within like the home domain, right? The computer at home with 16 or 32 gigs of RAM. So it's very plausible that you could be loading in something that big into memory, and you don't always need to have it there. So if you code the way you've been coding, you have to reserve that memory all the time your program is running, which may not be the most ideal way of doing it. If you use these dynamic variables, you can allocate it on demand. So A, you don't really need to know how much space you need ahead of time, and B, when you do already need to require some additional space, you can allocate it then, use it as much as you want, and when you're finished with it, you don't need to terminate your program. You can just sort of return that space to the operating system and then go on your merry way doing the rest of your code without hogging the space until your program finishes. So it's very useful when it comes to actually saving some memory. And it's very important because at the end of the day, your program is not the single one program that the computer is going to be running, unless you're working in a special project that maybe you're working on like an embedded system or something. And even then, you're probably going to be tight on memory. So that's one of the big powerful things with dynamic variables. It's that you are able to kind of take and return on your terms when you want and optimize your program in terms of space. So vectors already do this for you automatically. So if you've used vectors in the past and you've been using dynamic variables, but other than that, the default arrays don't do that. Default arrays are fixed. Now, if you've written a program like this in the past, something like int x, and then you say like cn x from like the user, and then you say like int a of size x. Technically speaking, this may compile in modern C++. Well, not may, it will compile. You might get a warning because technically it's not supposed to be good to do the syntax. It's not a static array though. It's just a dynamic array, but it's sort of being hidden from you because it's the compiler's just like, sites, they're not doing the right way, but we'll take it anyways because we know what they're trying to do. But outside of this, like this is technically not again, in the old C++, this wouldn't work because it's not right. You don't know how big the array is at compile time. And all variables, types, and sizes of arrays must be known at compile time unless you're using dynamic. That's just one of those basic things that C++ sort of decided when they came up with it. So yeah, this is basically a workaround to this. Even if you have done workarounds, this is the proper way, the OG way, I guess, when they first decided to allow dynamic stuff of doing this. Okay? So now I'm going to be showing you two brand new operators in this class. And the operators are going to be to create and to destroy these dynamic variables. So when you create them when you need them, get rid of them when you don't. Proper terms we like to use is not create, destroy, but allocate and deallocate. Okay? However, the operator names are not that. they are known as new and delete. So I'm going to draw a line here and then just kind of bring them both. Okay, so on this side I'm going to put the new operator, and on the other side here I'm going to put the delete operator. Now the name delete is a little bit misleading, because when we think of delete we're thinking of erasing, and by no means is the delete operator erasing or deleting something. It's merely deallocating, and that's going to come back to bite us if we don't understand. Okay, so just we'll keep that in mind for now. All right, so this is your to create and to destroy. All right, and these are reserved C++ words, so you can't create a variable called new in C++. If you ever try that before you knew what new was, maybe you're writing a program and you wrote that as a variable name and you got some weird error, well, now you know why. Okay, so let me just go on and show you how to use these and then sort of explain what is happening in memory. Okay, so to create a dynamic variable, the syntax is going to be the keyword new and then the data type and a semicolon. Okay, so this is going to actually allocate memory for you based on the data type that you tell it. And that's because things like integers, we said, have 4 bytes, but things like double have 8 bytes. Depending on your OS, for the integers could be more than 4 bytes, but still, let's just go with the basic way. So you need to know how much space you need, particularly if you extend this into using classes. A class variable may contain a lot of more bytes than that, because it might have like a couple of integers in there, a couple of doubles, maybe even other classes inside of it. So the size is going to be dependent on what that type is, and so the new operator requires that because it needs to know how much space to allocate for you. One example that I tend to give out in tool 2 for like allocation and deallocation is like, and since Vegas and all, is hotel rooms. You can think of the operating system as the lobby person in the hotel, like front desk. When you want to check in the hotel, you go to them and you say, "Hi, I would like to have a room." And then they say, "Okay, for how many people?" And then you're like, "Well, I just want to have one for myself." And then they're like, "Okay." They give you a key with a number. That's going to be the location of where that room is given to you. You have no control over what that room might be. Now, in the real world, maybe they're like, if you told them, "Hey, I've stayed here before, can I have this room?" Give them like a tip or something, they might. Or I guess an upgrade. But I'm just saying in a normal scenario, okay? Like, you don't have a control over what room you're going to get, other than like you're going to get a room for the amount of space that you require, right? And so it's the same way here. You're requesting a room per se to store your data, and the size of that room is decided by looking at your data type, which is going to tell you. You can think of it like the data type of a human is they're single, or they are a couple, or they are a family with one kid, I guess, something like that. Okay, so that's your data type per se. Okay, so anyways, that's the syntax. It's very straightforward, although if you just go in and throw it like this, it's kind of gonna just, you are going to succeed. You are indeed going to allocate a single variable using the above syntax, but it would be the equivalent of like you asking for the room, and then you leave the front desk, and when the room gets given to you, they just dump the keys in front of the front desk, assuming you're going to come back for them, and you never do. So at that point, the room is reserved to you, but you never took the keys, so you don't even know like the room was reserved. And worse yet, even if you did, you don't know what room it is. So good luck finding the room, particularly without the the room number. So this is where pointers come into play. Remember what pointers are. Pointers keep addresses. They keep addresses. In fact, you have the address of operator, which gets you the address of an existing static variable. But in general, pointers, all they are is just a variable that can keep addresses. Just like integers can keep whole numbers, doubles can keep floating point values, or well, floats can keep floating point values, doubles can keep double precision floating point values, cars can keep numerical representations of the ASCII, of alphabet using the ASCII rules. Pointers keep addresses as just byte representation. So because they keep addresses, and what you get when you allocate memory is an address back, which is your room number, that seems like the perfect thing to store in a pointer variable. And so that's basically how it works. New allocates a new slot in memory for you, a new room in the hotel, and you store that in a pointer variable, which is meant to store addresses. So that way in this pointer is going to be the location of the room you got. Okay? So you can think of it like your wallet has a special spot to keep the address or the number of the hotel, like the room number. And that's where you put your room key with the room number or something. That is going to be your pointer variable. Okay? And so what you need to do in combination with using new is also have a pointer variable ready to go to store that address that new returns. Okay? So what that's going to look like is going to be like this. I'm going to show you two-liner version and then the one-liner version. Okay? So first, make a pointer. Remember, you have to use the dereferencing or indirection operator, which is this little asterisk, to indicate that this is a pointer variable and not just a regular integer variable. But once you do that, then you can use your new call and the assignment operator to create a dynamic variable. So you can do it this way as a single line. You could also do it just like this. So both of these are the same thing. It's just, two lines versus one line. And I mean, it's the same thing if you think about like a normal variable, right? So like you could do like int x, and then you can do x gets 5, but you could also do int x gets 5, right? So both of those are like legit. In fact, I should just use that syntax here. Yeah, there you go. Looks cool. Although now I'm gonna run out of space, but yeah. Scroll this down a little bit. Oh, damn it. I broke the int. Hold on. Okay. So again, to make sure that we're on the same page here, this is a pointer variable. And this here is me assigning the address of the integer that we're allocating dynamically to that pointer variable. You might be asking yourself, why am I not using the address of operator? That is because this right here, the new call, returns to me already an address. So it's an address already. So I don't need to basically modify that value. It's like, imagine a function that returns an address. It's already ready to go, so I don't need to like cast it or anything. So that's why you're just seeing an assignment here, okay? You could, in theory, do something like cout, and maybe we'll do it in a little bit. You could say cout new int, and you would get just a hex address back out of this. Of course, you're not, it's gone, and every time you run it, you're gonna get a different address, because like it's like every time you send a hotel, you're gonna get a different room. But other than it's like if a person would, were like Memento, like the guy has like a short-term memory, like forgets everything after the day ends, right? It's like you get a hotel room and you get the key with the room number and you yell it. They're like, oh, I'm in room 501, and then you don't store it anywhere else. You just drop the key and drop the number, and then you forget because you never wrote it down. So That's the equivalent of that. That's why you're using your pointer, because that's you writing it down in a place that is meant to store addresses. Especially because, like, you might forget what that number even represents if you didn't know it was an address, right? Okay, so that's how you dynamically allocate a variable. Let's talk about allocating an array of variables, which you could also do. It's a small modification to this. So if you want to make an array of a dynamically allocated array, what you do is you write the word new, you put your data type, and then you put your basically your numerical expression that's going to initialize this in terms of how big you want the array to be. So an example of that, let's say we're using a car. So let's make a car pointer. So we want to make a character array, kind of like a string per se, like our own version of the string. At one point I made that an assignment. You know, fun times. Might bring that back someday. Students have to make their own string class essentially and use dynamic allocation. It's good practice. Makes you respect the string class too, because there's a lot of nitty-gritty things you got to think about. But yeah, so here I'm making a pointer. Now this is a character pointer, so it's going to be, well, nowadays it's technically you only need 1 byte for a character, but it's not going to take 1 byte in memory. It's probably going to take 4, unless you have 4 of them together. Then it tries to optimize it and put them all together in the same sort of row per se in memory, because memory says it's increments of 4. So like, think of it that way. So if you have a single character, it's probably going to take the entire 4 bytes. But if you have like a static character array, then it will fill like 4 of them here, and then the next 4, and so on. But anyways, don't worry yourself with those kind of things. As long as you say car pointer, they'll handle it. But yeah, so if we want to make this variable store an address of your brand new allocated array, all you gotta do is say new, the data type, which in this case is character, car, and then your expression, which we're going to say we're going to make it size of 5. But this could be, and that's why I wrote like int expression. This doesn't have to be a number here. Like, you don't want to hard code that. Why? If you're hard coding it, then why are you using dynamic? Like, you should be just using a static one, right? Like, the whole point of this is that you want that to be something variable. You want that to be a number that changes at runtime that you don't know during compile time. Or I guess if you could still make it you could still hard code it, but you're only going to make that available for part of the time the program is running. I guess that would be a fair reason to hard code it. But again, usually you don't want to hard code it because you have the flexibility to decide at runtime how big you want it. So, but yeah, point is, you put either some variable that's going to hold a number, or you just put the number directly. And this is making a dynamic array of size 5 and return to you the address of that. Now, what do I mean by address of that? Usually what ends up happening is you get the address of the first spot of the array of 5. So in memory, it's going to actually give you a contiguous block of memory of size that you want it. So 5 per se. Again, don't worry how this is being done internally. Just think of it that way. So you got 1, 2, 3, 4, 5. And technically speaking, what you're getting back from the new call here is the address of that first element. That's just the way it works. It's the same thing with a class. When you make a pointer to a class, you're getting the address of the beginning of the class, the first variable of the class that's in the class. So you can, which I think I said that in another video. You can take advantage of that to do some hackish things. So we'll play with that at some point. Okay, but yeah, so this is going to be your dynamic memory allocation of your single variables or your arrays. Now, everything that has a beginning has an end. Neo, it's like the teaser for like Matrix, I guess, Revolutions, the third move Matrix. However, it's true here. If you create a variable, at some point you'll have to destroy it or deallocate it. Now, with a given exception per se, Technically speaking, when you're running your programs and you allocate dynamic memory, or just any memory in general, when the program terminates, the operating system will clean up after you. So if you still have any memory allocated dynamically, it will go there and clean it up. So it'll delete it all, deallocate it all. So you don't have to worry about it per se, technically, but it's not a good practice, like to not deallocate things yourself. It's like think of it at the hotel. You're checking out of the hotel. One way you can do it is you can do your checkout, or simply check out, like say, okay, I'm done with the room, so you're free to clean it up. Even if like right there your program ends, or like you just leave the country, let's say that's the program ending. Even if you hadn't checked out, the hotel knows a way to know if you're in a country per se. Okay, so the program knows that you're still running or you stopped running. The operating system knows. So like once it knows you finish running or you crash or something happens, it'll automatically clean up for you. It's just like etiquette per se. You want to deallocate things, okay? But still, I'll argue that if a program is immediately about to end, in theory, you don't have to deallocate it. You, in theory, would be okay, but it's kind of looked upon kind of negatively if you do that. There is a program known as Valgrind that I'm going to show you later today or maybe in the next video that is meant to check for some of these memory issues that we're going to talk about. And for that to do a good job, you do want to deallocate things before the program ends, so it doesn't flag those as things that like should have been deallocated at another point in time, but we're still there at the end. Okay? So we'll come back to that. But for now, what we want to do is, how do you deallocate memory? So how do you check out of the hotel? Well, you're going to use a delete operator for that. And it's really trivial. All you got to do for the syntax is write the word delete. Oops. And then the identifier of the variable that has the address of what you want to delete. Okay, so let me repeat that again. When you want to deallocate a variable or an array, although the array one's a little bit different, but at least for the single variable, if you want to free that memory, return it to the operating system, all you got to tell the operating system is what you are deallocating. And what is that? Well, it's an address. Again, everything is stored by addresses. It's your room number of the hotel. All you got to do is tell it what that address is. What holds addresses? Pointers do, right? In fact, the pointer you probably used to store the address in the first place can be used again. But it doesn't have to be. It could be a different pointer technically, as long as the address is what you're actually wanting to deallocate. So just call delete and then pass that address in the form of a pointer typically. Okay? So an example of that, so let's say we were trying to deallocate our P here. What you would do is you would simply say delete P. Okay? And what that is doing is deallocating. A single variable. Okay? So that's what's happening right there. It's deallocating a single variable. All right. What if you want to deallocate an array that was dynamically allocated? It's very similar syntax. You would write delete. There's the ID stuff again, which is that address. But you have one more thing, and this is a little trippy. Like, I think the first time I saw this, I was like, huh, okay. But it just grows on you. You just get used to it. But yeah, it's the syntax. So you would delete, you write the array brackets with nothing inside, and then you put the identifier, which represents the address of what you're trying to deallocate, which is going to be that array. So let's look at the syntax of that in the example that we have here with the array of characters. It's going to look like this. Delete, square brackets, and then the pointer, which is p bar. And again, this is going to deallocate a dynamically created array, or dynamically allocated array, I guess might be a better term. Okay, or just dynamic array. I don't like the word created in there. It seems kind of fluff. Like that. Okay. So that is telling the operating system, like, hey, I'm done with this. You can have it back. Do what must be done. Do not hesitate. Show no mercy or something. I don't know. Okay. So that's it. That's dynamic variables. That's how you make them, how you get rid of them. That's almost the end of the story, actually. Now we got to talk about the problems that arise when you're doing this, okay? But just to triple make sure you understand this, deallocation is not the same thing as deletion or destruction per se, okay? Deallocation is merely checking out of your hotel room. It's merely saying, hey, I'm done. By no means would it be the equivalent of you, like, I don't know, blowing up the room, I guess, or like, you know, throwing, like, I don't know, what would be this? Yeah, like blowing up the room, okay? The room is still going to be there. Like, you leave the room, but it's still there. In fact, nowadays, a lot of the times when you check out a hotel, you get the little cards, right? The little malloc cards, and they don't even ask for them. So in theory, in fact, I'm guilty of doing this recently, actually. I checked out of a room, and I was in my car. I went with my mom and to Disney, actually, and so I went with her, and she's a little bit older, and so she's not as tech savvy. So she has an iPad, or no, I think it was a charger for the phone. She forgot her phone charger, so I let her use like a phone charger, and so I plugged it in for her and plugged it into her phone. And so when we were checking out, I was in the car already with some other family members, and so I was like, oh, okay, you'll get everything? And then I'm like, did you get the charger? She's like, oh no, I thought the charger was like a thing in the room, like the USB was like part of the room or something. Like, no, that was my charger. And I already checked out. But I still had like one of the keys because I did like the mobile checkout, so I still had the key. And so I was like, well, I guess I'm going back in there. So I go in, and like there's like a massive line in the lobby. So I was like, okay, I guess we're going in, rogue. So I went back up to the room. My door still worked. My key still worked. I was very careful to make sure no one was inside. I mean, I literally just done the checkout like 10 minutes ago. But I want to make sure like no cleaning or something wasn't there. And yeah, my charger was in the wall. So I went in, like took it, and was really angry on the way back to the car, but I was like, I'm gonna hold it, I don't, I gotta sympathize. I gotta be the nice person. There's no reason to like be angry, especially, you're coming out of like Disneyland and you're like, I don't want to ruin the trip or something, and like angrily try to lecture someone. So that was the end of that, actually. As you can see now, I have like PTSD from that or something. No, but yeah. So moral of the story is, when you check out of a hotel and you still have a key, that room didn't go anywhere. It's still there, and you still remember the address of it. And even though it's no longer assigned to you, if you still know the room number and you still have access to it through a key, nothing stops you from potentially going back in there, right? At some point, there's going to be problems with that, such as like, okay, what if you come back? Well, suppose they don't change the keys and they still work in the future. Suppose they come back in like 2 days and there's like people in there and you go in there. That's not going to end well. Or, there's cleaning people in there as well. So that is a potential issue, right? Security issue amongst other things. And the same thing actually happens with programming. When you deallocate a variable, you are just telling the OS like, hey, I'm checking out. But more than likely, so in these two scenarios actually, you still have the address of that variable. So you still have the room number. And in C++ land, I guess you can think of it as like utopia. When you get a room number, all rooms are unlocked. The only thing you need to be able to get in the room is just to know what room you're going in. So that makes it very risky for you to access the wrong room, but also to access the right room after you giving it back accidentally. Okay? Now, you might say, oh, I'm never going to do that. But, well, both either in the real world or in programming. But, I gave you an example of, I guess, when in the real world that happened. But in programming, it's so easy to accidentally access things that you already deallocated. And that is a major problem, because at that point, you don't know what's going to happen. That could have been allocated to somebody else. That could have been reallocated to you, to a different variable or a different part of your program. Or the operating system might, it doesn't like you accessing other people's memory or other programs' memory. It might just be like, it might just catch you in the act of breaking into somewhere you shouldn't and literally terminate you, as in like, end your program. Okay, not like terminate you like, yeah, no terminators or something. Okay, but yeah, so that is what is actually known as a dangling pointer. Okay, and that is one of the two risks that appear when it comes to memory issues that you can run up there. And the other one is going to be memory leaks, which is, well, they're both bad. I don't know. It would be weird to say one's worse than the other one, but I'm going to go out and say that memory leaks are actually worse, okay? So how do you stop that? But let's finish talking about the dangling pointer one, since we're already here. How do you stop that from happening? How do you stop from accidentally going back into the room that you shouldn't? Well, in this scenario here, so like, let me just kind of put it again down here. So let's copy, where's my one-liner? I want the one-liner. This one. Well, and by the way, I didn't do the one-liner for the array, but I assume you know that, like, yeah, this can, here, let me just copy paste it actually. I'll delete it right after, but like, if you want to make the array into a single line, all you gotta do is just basically bring that down like that. And there you go, right? That's a single line dynamic array allocation. So, yeah, I'm pretty sure you would have figured that out, but it's nice to see an actual example. So, I'll just leave that here. Okay, but anyways, we're just sticking to a single variable for now. So we got our single variable, and then you do whatever with it, and so there's some code here, and then eventually you're like, I'm gonna go and give it back. So you say delete p, and then you just keep going on with your life. But at some point, you accidentally either assign something to p, like this. Obviously, you need to use the dereference because you want to assign it to the where p is pointing to, because remember, p is just an address. Or you're actually still accessing whatever used to be there, or both actually. So you could do both. Three things can happen here. One is it works and nobody knows, nobody knew, everything goes on, life goes on. It's like I go into the room, get the charger out, nobody knows, none the wiser, life is good. Other thing that happened is at least for assignments. You override somebody else's data because that room was already assigned to somebody else. So, but you don't know that you did that. So you can corrupt others' data. It might have changed in the meantime. So like this could have been assigned to someone else. That someone else was modifying it. And then when you go and see out it, you're getting some random, like weird stuff in there. So that could happen, which is also really bad because it's undefined. Or worse yet, well, again, not worse, this is all bad, but your program just crashed because the OS catches that this no longer belongs to you because it assigned it to somebody else. Okay? More than likely, though, you're going to get the first scenario, which is like you'll be able to go in there, do what you want because you forgot something and be okay. Or in the case of this, accidentally access things you shouldn't, or keep using a variable that you was no longer allocated to you. In most, like I would say the majority of the time, the OS is actually flexible enough to not reassign things, and that will be the result. But this kind of goes into the land of what's known as undefined behavior in C++. The C++ designers, the architects per se, they had to decide what things were allowed and were not allowed, but they couldn't, they couldn't put every single case that somebody could ever think about. So it's like some things were just kind of left to the developers of the compiler to decide how they wanted to do it, and they didn't put a rule based on it. And they call that undefined behavior, meaning that the C++ rule book person, the C++ constitution, does not define what should happen here. So it is up to the individuals who are developing the compilers and the interpreters and everything to like decide how they want to handle that. Okay? You don't want to do undefined behavior code, because at that point you don't know what's going to happen. And if you're writing code that somebody's life depends on it, like this is managing like a hospital's like a breathing machine or something, you want to make sure you know what is going to happen in that code at every single moment. You don't want to have a scenario where like, well, it might crash, but it might also work fine 99% of the way. No, I want to have 100% of the way. Like, I want this to be like robust, because if somebody dies, that is negligence on you for not checking the code potentially. So yeah, that's actually one of the big reasons why it's a good thing to fail sometimes in school, because you learn lessons in school, and at worst you just get a bad grade. Nobody's going to care about a bad grade in this class 20 years from now. Okay, like honestly, no one's going to care. Don't feel bad if you ever get a bad grade in a class. Like, no one's going to really care. At worst, I'll ask you about it and it'll be a good laugh. Okay, but yeah, however, if you write some code like the Torak 25 case, I think that's one case that literally results in death of multiple people, then it's not going to be just something that no one's going to care about. You're probably going to end up in jail, and yeah, well, maybe they have death penalty, and death penalty, like, I don't know. But the point is, it will not end in just like a shrug. It's going to go further than that. So it's better to kind of learn here and fail here, so that you learn from those failures and you don't repeat them in the real world, okay? But that aside, what I'm trying to get to is, if you access dangling pointers, you're playing with fire, so don't do it. So how to stop you from doing it? Because if you knew that you were doing it, you wouldn't do it. And that's the problem. You don't know that you're doing it, okay? You don't know. You're like, right now, this is like, oh, this is so obvious. Like, I have deleted and then I have this beneath it. Like, why? Yes, because it's like a baby example. But like, there could be a lot of factors that make you not see that when it's happening. And that's the problem. It's because you don't know that it's happening, okay? That's that negligence. And just because you didn't know you were doing this and you didn't know this could have happened does not exempt you from like potentially having criminal negligence when you're writing code. Okay, that's important too. So, how to fix this dangling pointer problem? Okay, so the dangling pointer is happening because of these lines. Well, the quote-unquote easiest way to avoid the dangling pointer problem is to assign null to a pointer after you deallocate what it was pointing to. In other words, all I gotta do to not end up in jail for negligence, I guess, is write a single line of code that says p gets null, or null ptr, or 0 even. Okay? This is like protecting yourself. This is like getting insurance, I guess, or something. Why? Because your program's still going to crash, but at least it's either not going to compile. Actually, no, it'll compile, but it's going to crash immediately when you launch it. Why? Because when you try to access address 0, the program just like says segmentation fault or null pointer dereference error or something. You've seen that. Video games, null pointer exception. That's what's happening. You're trying to access a pointer that was set to 0. Why was it set to 0? Because you probably started initializing it at 0 and you never used it, so it's still 0. Or after you deallocated what the contents of the pointer was pointing to, you set it to 0 to avoid risking a dangling pointer. So that's how you catch it. So you fail at this stage so that the error doesn't slip by and then crashes only once in a while, because those are the worst kind of crashes. You know, if you have a bug in a program, the first thing you want to do is to fix it, is to be able to repeat it. So you have it in a closed environment and you can repeat it, because then you can try to fix it and then see if it gets fixed by repeating what used to make it crash or something. The worst kind of bugs are the ones that sometimes happen and sometimes don't. Then you're pulling your hair because you don't even know how to repeat it. So how do you know if you fixed it if you can't replicate the bug? It's a pain. You don't want to go there. Trust me. It's it sucks. So simple line of code, but does a lot. And basically, it stops you from remembering. So if you look at how memory is, let's kind of go line by line. So the first line, int p gets new int. You have a static variable. So this is a static variable in the sense that it's not dynamic. Now, I guess I should point this out. The word static in static integer, like a class, or just a static variable in C++, you can think about that as adding the word static in there, is different than when I'm talking about static as in memory. Okay. So static in memory means that it's a variable at compile time, and then dynamic is runtime variables. That's static versus dynamic. It's not to be confused with something like a static variable in a class. That's a completely different story. So just be aware of that. Okay. So what I'm saying is, within memory, p itself is static. It has to be created when you create the program at compile time. You actually tell it that you're going to need this variable. And so when the program starts, it's already there for you, and it persists until the program terminates. Just like if you did int x gets 5, okay? However, the stuff that you're doing dynamically, so this right here, that's a dynamic variable that's only going to persist from there all the way until the delete line, okay? So that one is going to, and it's also going to be wherever the lobby people tell you, whatever the OS says, this is your room, that's what you get. So let's just say that we get address 550, okay? So address 550 there, it's in hex. Because you're saying int p gets new int, that means that here is going to be stored address 550, okay? So then you have code, blah, 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 a bunch of code. You use this value, you store information in it, do whatever you want, done, 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 probably in a loop. And then it comes down to deallocate it. So when you say delete p, all you're doing with delete p is it's sending a command to the OS to basically free this memory. Okay? Let's say that somewhere in here there's a 55 stored, or not a 55 because I keep using 55, but a 20. That 20 is still there. When you say free, or you say deallocate, delete, all you're simply saying is, hey, I'm done with this. You're free to do whatever you want with it. The OS does not immediately go in there and clean up the contents, so that 20 still persists, which means you can still access it later. So when I check out of the hotel, they don't immediately go in there and ravage clean the hotel that second. They might do that later. You have no control again over that. It's undefined behavior. But the point is, just like in the real world, they don't do it immediately. So I could go back in there and get that information out, even though I had already returned that room to the hotel per se. Same here, you could accidentally access that 20. Hopefully it's accidental, not intentional, because otherwise why did you deallocate? So that's not a good thing, again, because that data might change between when you deallocate it and when you go and access it again, which means you could get invalid data or just crash. But yeah, that's what's happening is you're freeing it. So then if I go in there and say p get 55, p still has the address of this, so I can go there and actually change this to 55. And I can also see out it, etc., etc. The difference is, when I do this line of code, p gets null, I'm changing the contents of p from 0x550 to null, which is just 0, or you'll see it as 0x0 sometimes. Now, even if you wanted to change or see the contents of whatever p had, you can't, because you lost track of it. It's go back to thinking about memento. You literally you forget about the day before. So, and if you erase any knowledge of something, you really lost it forever. So this is good, because now you can't accidentally go back into whatever p was pointing to. You can't go back to 550. And remember, this 550 changes every time you run the program. If I rerun this program, it might not be 550, it might be 650. So there's just no way of knowing where. And that's a good thing. Because again, now that you set it to null, you can't accidentally access something that no longer belongs to you. Okay? So I think I repeated that enough times to make sure that you understand it. I am emphasizing this because it's important that you understand it, because you want to avoid accessing dangling pointers. Okay? All right. Now moving on to the other major issue with memory leaks. Let me just start out by giving you a situation that's going to cause it. Okay? So let us say that you have the following piece of code. Okay, you're like, yo, I'm learning pointers, so I'm going to go ahead and make a pointer variable. Then I'm going to dynamically allocate a variable and put the address of that in P. Okay, so what's happening in memory is somewhere in here you got P, and somewhere in here you're going to get, let's just say this is address 150. You're going to get assigned by the operating system as what P is pointing to. So that means here you're going to get address 150. Okay? Then you're like, ah, this is so cool. Let me try to change what's in the dynamic variable that I just made. So you say something like P gets 21. So P currently has address 1500. You dereference that address, which means you go to that address. So you go over here and you put 21 in there. You're like, oh, very cool, very cool. Let me see out it to see confirm that it worked. You're like, my experiment has succeeded. I have been able to print out 21. Great success. Okay, so you do all that and you're so hyped about this. You're like, let's make another dynamic variable. It's like, yeah. So you go in there and you say P gets new int. And you're like, now there's two of them. This is getting out of hand. Okay, so what's happening there? Somewhere else in memory, like maybe down here, address 160, not to scale, by the way. Somewhere in that address, you just get those 4 bytes of memory. So now P contains the address of the new variable you made, 160. Okay? And you're like, oh, this is cool. Let me try storing in it. And you're like, let me try putting in 42 in that one. And so what happens there? The reference 160 and then throw in 42 in there. And by the way, when you first make the variable, it could contain garbage. So be careful of that. As always, initialize any variable you make. So in theory, if you want to play it safe, right beneath this, you should saying P gets like 0. I don't know, initialize whatever you want, but initialize it with something. Or just put the value that you want immediately after. So just remember that. But anyways, it's not what we're getting to. You're like, oh, this works so cool, I'm going to see out it to see if it worked. And you're like, oh, so hyped and everything. So cool, right? And then you're like, I'm going to go ahead and clean up after myself. I'm going to return these. I don't need them anymore. So you go and you say delete P. And you're like, well, I did all my cleaning. I can move on with my life now, right? Well, what is delete going to do here? Well, P is containing an address right now. It's containing address 1660. So when you say delete P, this here is returned to the OS. So it's like free, return to OS. So you have deallocated one of the variables you created. But you still have the other one. You still have one address 1500 allocated to you. And worse yet, you have no way of accessing it anymore. In fact, you lost that address. When did you lose that address? Well, you lost the address right here because you created a new variable and you stored the address here, which could previously contained the address 1500. Right here, you replaced it. So that address is long gone. Guess what? You have no way now of going back and deallocating that because you don't know. You're like, oh, I wrote it somewhere. Where did you write it down? Like, I mean, it's nowhere in here. It's only here because I'm telling you, because, you know, I did you like the visual aid, but like nowhere in here is there record of that address. And remember, every time you run the program, it's a different address. So like you have no way of accessing it. So this right here is what's known as a memory leak. You have memory allocated to you. So like the operating system has given you this memory. The hotel has assigned you this room. And then you got a second room. And it also assigned you that. And you can get as many rooms as you want. But you got to return them at some point. And in this case, even if you wanted to, you can't. Because you forgot what room number it is. You're like, oh, shoot. Okay. So what's the only way that you're going to get that memory back? When the program terminates and the OS cleans up everything you left behind. Remember, that's one place where the allocation happens. So in theory, this room is going to be hogged up to you until the program terminates. Now you might be like, whatever. You know, this is like some like 1,000 room hotel. What is one room going to do? When I'm done, they'll get it back. Big deal. And sure, I will agree with you that like it's not going to make a big difference in like the optimization of the system to just have one lost room for the duration of your program. But unfortunately, this stuff is usually not isolated to like a single scenario like this where you just have one leak. Most of the time, a lot of the code that you're running is code that's running in a loop. And if you have a code like this, every time it loops, it's going to create one more room that it's going to leak, basically. And so what ends up happening in a lot of the programs is that memory leak slowly grows. Well, sometimes not slow, but, well, I'll say this. The harder to detect ones are the slow ones than the ones that grow quickly. And so your program will run fine, but every time it allocates one room, it's like taking away from other programs that could be using that memory. And not just other programs, but even your own programs. It's lost for everybody who's sharing the system that you're working with. As this grows, one tiny spot, but if it's looping repeatedly and it's growing over time, it's going to get to a scenario where like you're literally going to have every single room in the hotel booked to you, but you have no access to them to return them. And eventually, either you are going to try to request one more room, and the hotel's going to be like, "Yo, I'm out of rooms, man. You got them all." Or somebody else is going to come in, like another program that's running at the same time, and try to request a room too, and they're going to be like, "Yo, I'm out of rooms." Now, in the real world, again, you learn more about this in 219 and 370. You know, it goes to the swap file, and things get really slow, so you may not necessarily crash, but you might. Especially if you go over a certain limit that a program can take of memory. And so, realistically though, what's going to end up happening is you're going to slow down the system if you just hog all the memory. Like, eventually you're just going to run out of memory, and it's going to start using, like I said, the swap file or the page file. So basically it's copying some of the contents of RAM into the hard drive so that it has more space on RAM, but that's a really slow process. So like you slow down the whole computer, and yeah, no, it's not a good side. I'm sure you've all experienced it if you've played any form of video game or video editing softwares or anything that uses like a little bit of memory intensive. And that's because memory leaks, while simple to solve in a simple example, are really, really hard to track down. Dangling pointers are hard to track down too. You would think not, but they're still sometimes tricky because like the way code is, it's not as easy. I mean, obviously I'd show you how to kind of fix them, but sometimes it's not as easy to do that as you might think. But the worst case scenario with memory leaks is that it's really hard to not see that you didn't fix a memory leak. And you can try to fix a lot of them, and you usually can like really do some good work with it. But given a large enough program, it is practically impossible to fix all memory leaks. It gets to that point. So that's not to excuse like game developers who write code that like has memory leaks that crash the program after 4 hours. But let's put it this way: that's one of the lower priority things based on the amount of work it would take to find that, which is basically like finding a needle in a haystack for things like that. So how do we fix a memory leak though? Well, we have to modify this code and do one of two things. you have to either, if you're not going to be using address 1550 like after this line right here, then deallocate it at that point. So I could go in and say delete P before I go and reassign what the contents of P are, whether it's to a new variable or anywhere else, even setting it to null. Make sure that you deallocate that first. And that's going to fix the memory leak here, because that'll make sure to return this before you lose access to it. However, if you still needed access to it, then you gotta either make another pointer variable and use that for the second variable you make, or copy that pointer to another pointer to store as a backup and then use the other one and then bring it back. There's a lot of things you can do if you still need access to it. So you can do those, or if you don't need access, then you can just deallocate it. Again, this is a toy example. Obviously, this is like easy to solve and there's no real critical thinking associated with figuring out a solution for this. It is by no means this easy when it comes to a real program, because you got things going in loops all over the place and thousands of lines of code, and things get allocated at one point and deallocated in different files, and you don't know what's happening half the time. So, you know, it's not as easy to in the real world. It's like rocket science, you know. A rocket is made up of tons of components, and if one fails, the whole rocket fails. And you've seen all the companies try to launch to orbit, and a lot of them fail, right? Or even companies that succeed, like SpaceX or Rocket Lab, had plenty of failures before they got to orbit. Did they mean to do that? No, they had tons and tons of quality control and checks and things and triple checking things, but they just can't check everything because it's just not humanly possible to like do that, right? So it's the same situation here. You do your best to avoid memory leaks, but unfortunately, they are still going to creep in. So for this class, you're required to not have memory leaks, because these are all, even your assignments are still toys compared to like real world programming. And we do want to teach you good practices, because the less memory leaks you do now, the less you'll actually do in the real world. And remember, going back to the life support system, you got a memory leak on like an oxygen machine it's in the loop. Imagine like every time the person breathes, it's like one loop. You have an integer leak there. After 1,000, how much is that? Well, that's about 4 kilobytes of leak. Okay. Now what about like 1 million? Okay. If you do a million repetitions, that's 4 megabyte memory leak. How many times does a human breathe per day? Let's say 15 per minute times, do some math, hold on. 15 times 60 for an hour times 24 for a day. That's about 21,000 times, let's do 22,000 times a day. Okay, so if you have a 4 byte leak in your program, and it's repeating itself 22,000 times, that's close to 100,000 bytes lost, right? The exact number is 88, but yeah, let's just round up to 100, okay? This is, of course, going to be 100 kilobytes, right? Okay, now what if your thing is running for a month? It's going to be 30 days, so that is going to bring it up to 3 megabytes, basically, right? 3 million. Am I doing that right? Yeah, maybe. It's late at night, but okay. 100 times 10 would be 1 million. Yeah, okay, I'm doing it right. That's 3 megabyte leak. Okay? Let's say that this is an embedded system and it only has 4 megabytes of RAM. You're already taking over 3/4 of the memory on your tiny little memory leak over the course of a month. But you're like, no, this thing has 32 megabytes of RAM. Okay, you're still going to kill the person in less than a year because the thing's going to crash and they stop breathing. So don't just assume that because your leak is tiny and you have a lot of memory in your home machine that every single device will have 16 gigs of RAM and it's going to be an insignificant leak. No, these things can grow rapidly. So you have to be careful about it. Of course, if this is a video game, you're never going to get even to the kilobytes. Like, you're never going to even get to a kilobyte because no one's going to be playing a game for like, well, most people are not going to be playing a game for like days nonstop, right? Unless you're like doing one of those like 100-hour Twitch TV streams playing on like, I don't know, random video game. But even then, it's like 100 hours. Like, that's a lot, but not enough for a tiny leak to make a difference, right? For those, you have to worry about the big leaks, because if your game crashes to 4 hours, then that's kind of problematic for a lot of people. So, yeah. What I'm really trying to make an argument for here is you have to be careful of memory leaks. Don't just be like, whatever. It's not that big of a leak. No. Have good etiquette. Always check your code. How do you check your code? Well, there's a tool called Valgrind, which I'm going to show you in the next video. But there's a lot of ways that you can just verify your code, okay? So, having said that, let me see if there's anything else I have here on my notes to talk about when it comes to dynamic memory allocation. Oh, yes, I do have some stuff. And I'm probably going to do that for the last few minutes, actually. Here we go. So, next class, I will go ahead and code some of this stuff so you can see it in Valgrind, which is to detect memory leaks. And I'm also going to code multi-dimensional arrays and classes and a lot of good stuff. But for now, I just want to show you how to allocate memory in C. Okay? So what I've shown you so far is C++. And you should be coding in C++ because that's what we're using in the class. But it's still good to know the C way because it does work in C++, and you might see it in somebody else's code, especially if it's like copy-pasting code from a C library or something. And I don't want you to be confused if you ever see it. I want you to be like, oh, I know how that works. And it also helps because it kind of helps you think about like how memory allocation is all about the size that you need. Because right now, I said like, oh, you do new int, and the OS like just knows that an int is 4 bytes, but like we don't really see that happening. It's just kind of magic. With C memory allocation, it's still magic, but it's a little bit less magical. It's like real magic-ish kind of. So let's just show it to you. Okay, so this is going to be memory allocation in C, the 10-minute version, because I don't want to spend too much time on this. It's almost the end of the video. Okay, so let me just go ahead and write an example out, and then we can talk about it. Okay, so I'm still gonna have my P pointer, and instead of doing that really nice and simple like new allocation, I'm gonna go ahead and do the C way of allocating an array. So in fact, here, let me show you what it would have been like if it was just doing it the method I just showed you today. So this would have been the equivalent of me doing P gets new int array of size 10. So an array of size 10. Okay, so this would have been the C++ way. The C way is going to be this way. So let me just write it first, and then I'll talk about it. Actually, I'm going to run out of space. Let me strike that. Okay, so there's that method, and then there's the easier method of doing it, a little shorter method per se, but it works. I think this one will only work in C. It might give you an error in C++, and that one is this one. So this one only works if you were coding actually in C. I don't think it'll work if you try to compile it in C++ because of the void pointer. So first of all, what does new return? I told you it returns an address, right? And an address is basically what a pointer is. So addresses, though, or pointers have a type in C++. In C, addresses are just addresses, and so you can actually have what's known as a void pointer, which is like a pointer that doesn't really have a type associated with it. It's kind of trippy to think about, but it's just a thing you do. And so in C, instead of using new and delete, you actually call functions to do your allocation. And the two functions that you call one for allocating, one for deallocating, is malloc for allocating. So this is your memory allocation function. That's malloc, memory allocation. And then if you want to deallocate, I'll show you that in a little bit, but it's just free, okay? So that function returns a pointer address. So it's a pointer, basically. The pointer is an address, okay? And it actually returns a void pointer because they just wanted to make the function like universal, so it works for any kind of pointer. So it just returns a void pointer, and then it's your job to convert that pointer back into whatever the type is if you need to do that. But in C, you can just store a void pointer, so you don't even have to. So that's why the one that works in C, the bottom line, doesn't have that initial casting. So let's kind of work our way from left to right. So this is our assignment, of course. This right here is just casting, right? Remember in C versus C++, casting is a little bit different. So like if you want to cast like a variable in C++, you write like the word static cast. You put the type that you're going to cast to, and then you put whatever you're casting from there. So like let's say you're casting some variable x that was like a double per se. Double 20. But yeah, so you're casting a double into an integer. You would do something like this, and then you'd store this in an integer variable, so like int y, right? That's the C++ way of casting, right? And we'll come back to talking about casting when we talk about dynamic casting and reinterpret cast and whatnot. But yeah, maybe in the next class. But now, actually, no, I have separate videos of those. Yeah. So yeah, so that's your typical C++ casting. However, in C, to cast, it's kind of nice syntax. I like it. You just use parentheses. You put the type you're casting to, and then you put where you're casting from. So it would look something like this in C. However, this will actually, I believe it'll work in C++. I don't even think you need parentheses here. Yeah, no, you don't. I think literally that is enough to cast in C++. It's known as a C-cast, I believe. So, I guess it's okay to use, but technically, if you're using C++, you should be using C++ syntax and whatnot. But this is actually kind of a weird syntax, as is. We will talk about this. It's actually a template. If you look in your schedule, there is templates in there. So we'll come back to visiting this sort of weird syntax like that. There's a reason for it. But yeah, so this is your casting. So that's where this is coming from. So this is casting whatever malloc is returning into an integer pointer. That's why there's a little asterisk after that. Because like here, it's just a normal integer. But here, it's an integer pointer. So when you want to cast something to a pointer, you put the data type, and then you put the asterisk to represent the pointer. So like, if I wanted to use static cast to cast a pointer, which you don't do, you use dynamic cast, then you would just put it as asterisk here. So we'll definitely revisit this whole casting with pointer stuff. Here, let me write it up here so it's easier to see. So this is what you would put inside of there. If you were casting like a different pointer to an integer pointer, you would do that. But again, you don't really do that in C++ because you use dynamic casting for that. So yeah, so this is what that's coming from. That it's just casting whatever malloc is returning to a integer pointer. So it's going from void pointer to integer pointer to store in an integer pointer, which is p. Okay? So now let's look at the malloc function itself, which is this part, the top one. So the malloc function requires the amount of space that you want to allocate from the operating system. Okay? So whereas in C++, it just knows. It's just like, I want an integer, so it just knows. Here, you have to literally give it the number you want, and the number is in bytes. So all you do is a little mathematical operation to figure out. If this was a single variable, all you gotta do is tell it how many bytes you need. So you could, in theory, put just a 4 in here. So say malloc 4, and like call it a day for an integer. However, this is bad because your operating system might use 4 bytes for an integer, but if somebody else uses 8 or less, like I think really old systems would used to be 2 bytes for an integer, like way back in the day before we were born, basically. So that wouldn't work there because that would be allocating too much memory and like bad things would happen. Or it might allocate too little memory in like future world where everybody has an integer of size 8. So to make sure our code is portable to any system, we want to find out how big an integer takes in that given system where you're compiling the code, which should be the one you're running the code in. So that we use another function for that. Well, actually, it's an operator in C. Is it a function or an operator in C++? I don't remember if sizeof is an operator or a function. I'm going to go with function just because it looks like a function in C++. And that's what's happening here is I'm like doing sort of like a mini function call, I think, and I'm checking how big sizeof is. Although I don't remember. I just know this works, but I don't remember if technically sizeof is an operator or a function in C++. Okay, but what you do is you write the word sizeof and you put in parentheses the type that you're trying to figure out how big it is. So what this is going to return, sizeof int, is going to be 4 in my system, and if like their system has integers with size of 2, it'll return a 2 for them. Now, because it's an array, again, if this was just a single variable, I would stop here. But because it's an array, what I do is I simply say multiply that number times how many elements I have in my array. So in this case, I want to make an array of size 10. So multiply times 10. And I think that part is kind of obvious because if you want to have 10 integers, then you need 10 times whatever the integer takes, right? It's like if I have a family of 4 and I want 10 rooms of this, then I just multiply 4 times 10 and I need basically room for 40 people. All right, so that's all that's to it. Pretty straightforward. On the other hand, the C way, which I just put as a fun fact, but just quickly, that one is definitely like a little operator in C. And all you're doing when you put it there is you put sizeof and then you put next to it the type that you want to sizeof. And in this case, because P is an integer pointer, it's checking the size of P of the size of integer and returning that. And then it's multiplying it. So it's kind of trippy. But here, like, this is actually multiplication. Just like this is multiplication. However, here, this is actually like the dereferencing operator. So that's like the pointer thing. So that's trippy because you have both operators next to each other. So that's like, oh, spooky. But again, that's the C way. Don't worry about that one. Use the top one. But I thought I'd make, actually technically here, this is your dereferencing operator too. So you still see both in the same line, which is kind of neat. But this one's just spooky because they're like next to each other and you're like, ooh, okay, scary. So yeah, but no fear. All right. So that's your allocation. And now we're going to move on to your deallocation. So when you want to deallocate in C, this one's really nice and simple. So don't worry. If you're like, oh no, we're already running out of time. No, it's easy. You just use the word free and you pass in the pointer that you want to free. So like P. And then of course, because you are a good, you got your good manners, or what do you call it? Yeah, good hygiene of code or whatever. You're just gonna remove your. You're gonna set it to null afterwards, right? To avoid dangling pointers. Right, because we just had a spiel about that. So you always want to set that to null whenever you deallocate, whether it's in C++ delete or C free or whatever. In C days, if you're actually coding in C, I don't know if null is actually like a keyword in C. So you might need to actually define null. So you can use a define for that. So you might have to say something like define null is 0, because that way, or you could just say P equals 0 too. But again, I don't like that syntax because that makes me think it's an integer when it's not. It's a pointer. So do this if If null is not defined in C, and if you're coding actual C. I don't remember. It's been a while. Okay? But yeah, literally just free. So this is kind of neat because like when you're working in C++, you need to know if what you're freeing or what you're deallocating is an array or a single variable. And that's going to define, right? Because like in this case, we know that the C++ version would have been like delete P, right? That would have been the C++ version. It's still nice because in C++ you don't have to tell it how big it is. Think about that. That's actually really cool and powerful. You don't need to worry about how big the array is. You just got to tell it it's an array. But you do got to know that it's an array. Because if it was a single variable, you would just say delete P. But that's going to delete just one variable. You're going to have a memory leak. That one's going to be more of like a real memory leak that you didn't mean, right? So it's a good example of memory leak that you didn't mean to, that might not be as trivial. If you don't know if that array, if whatever this pointer is pointing to is an array or a single variable, if you try to call delete as a single variable and it's an array, you're only going to deallocate part of it and the rest is going to be a memory leak, which is probably pretty bad if the array is big, but just in general it's bad. Or worse yet, if you're like, oh, let's play it safe and call delete on the array, but it actually was a single variable, that's really bad. When you try to deallocate memory that does not belong to you, is like trying to check out other people in the hotel that is not you. You're either, again, going to crash or it's just going to give you some nasty, nasty errors. But more than likely, you're just going to crash with some nasty error. Nasty, nasty. We'll see you next time. But yeah, I'm going to get rid of that because I don't want to confuse people. But yeah. Okay. But in C, it's nice. It's like it'll handle it. You just like free this and handle it. And so you don't have to worry about whether it's an array, single pointer, a single variable, nothing. It will handle it regardless. So you're like, yes. Now, because of that, I've seen a lot of people when they're coding, they use new for their allocation, and then because they don't know whether it's, or they're having bugs because they don't know if it's an array or not, so they just use free. That's really bad. Don't mix C++ and C memory allocation operators. You do not mix them. It's technically okay in your program if you allocate stuff with malloc and then deallocate it with free, but that should be self-contained. Do not mix like allocating stuff with new and then deallocating with free, or allocating something with malloc and then deallocating with delete. Keep them all together. Okay, so like malloc and free, new and delete. Keep those connected. Never ever do something like do not do this. Do not crisscross, okay? Like don't allocate something with malloc and then deallocate it with delete, or allocate something with new and then deallocate it with free. You do that, some really nasty bugs are gonna happen. I don't even want to roll that. I'm not even going to show that case. You go and explore that on your own if you want. But no, it's nasty. And just no. Just don't do it. It's like, don't do it. Some things you do and some things you don't. And this is one of those things you don't. So, yep. All right. So that's it. I know that this is a C++ class, but you don't really need to know C. But I do think it's useful because you do run into it a lot. And now you know how to read it and how to fix it if it's a bug. And particularly how not to mix free. If you go on Stack Overflow and like someone's like, yo, I know the solution to your problem, just call free. And then you're like, you do it and it kind of works, and no, it's like a time bomb. Okay? So not to discredit Stack Overflow, there's some great stuff there, but you have to understand the basics to be able to understand what's the good stuff and the bad stuff there. Okay? So that's my lecture for today. Now you know dynamic variables. Now you can make your arrays on the fly and delete them when you don't need them, and you will never ever have memory leaks or dangling pointers, right? Well, at least that's what you should aim for. Realistic versus expectations versus real life kind of thing. All right, so thank you all for watching, and in the next video we will get to play with all these things. So stay tuned and see you next time.